I guess it's past, so I should probably get going. Hi, my name is Paul Durrant. I'm Senior Principal Software Engineer at Citrix and Community Lead for the Windows PV driver sub-project of the Xen Project. And today I'm going to talk about what's been going on recently in the general area of network performance in the Windows PV drivers. So I'm going to go through a little background first about the various changes that have been made to the Netif Protocol, which is the PV protocol, over the years. And I'll also give a little background on what Windows RSS means. We'll then look at extensions made to the Netif Protocol to allow Windows RSS to be supported. And then we'll take a look at some performance measurements I did. And I've left a slot for QA at the end, but we can take a few questions as we go. So first, some background. So the Netif Protocol. The location there is where the canonical header for the Netif protocol is. That is the source of documentation and the definition of the protocol. In general, for PV protocols, you have to be aware of looking at the headers in the OS you happen to be developing for, because, well, for instance, the Linux one, before I updated it recently, had lagged the canonical one by some distance. It was quite out of date and was actually missing documentation for Xen keys that were already in use by the Linux net-back drivers. So always go to that version of the header file to check for the latest updates. The protocol is like most other protocols in Xen, PV protocols in Xen. It's a shared ring, requests coming from the front end, responses coming from the back end, pointers chasing each other around the shared page. But obviously, RX and TX in a network environment not being balanced, you can't just do single request response. You need separate rings for transmit and receive. Now, one thing to be aware of in the receive ring is that the requests still come from the front end. So it's not like a packet comes into the back end and the back end issues a request. No, you have to pre-fill the ring with the requests from the front end, and they get completed as responses when packets arrive in the back end. So you have to stump up some memory up front to fill that RX ring. So the packet structures are a bit odd. They have some quirks, which I'll hopefully explain a little bit here. So the general layout of a TX packet is as displayed there. It's a chain of fragments, as you might expect. But buried in the middle of the data fragments is this potentially list, at least, it could be just one, but it could be more than one extra fragments. Those go strictly between the first data fragment and any subsequent data fragments. There may be no subsequent data fragments, but that's the position in the chain they sit. Extra fragments are there for carrying metadata about the packets. So for instance, in a GSO/TSO packet, you'd have a value for the maximum segment size that the GSO needs to be fragmented into, and that will be carried in a metadata extra fragment there. Now, one quirk of the TX packet is that the size of the first data frag is actually the size of the total packet, not just the size of the fragment. So the back end has to read all fragments from the front end and then calculate the size of the first fragment by subtracting all the others from the first one. This is a bit weird, but that is the way it works. So beware of that if you're ever writing a front end. Data frags coming from the front end carry an ID field, and that is echoed in the response for the corresponding request. So when the back end completes a TX request, it fills in the ID field in the response, so you know how they tie up. However, extra fragments don't have an ID field in them because they had to repurpose the ID field for other data because they're a bit small. So how do you tell which is an extra fragment and which is not an extra fragment? Well, that's done by a magic status value. So if you get a completion coming back with a status of RSP null instead of OK or failed, then you know it's an extra fragment, and you should just, you can decrement your reference count stuff. And you don't necessarily need to know the ID coming back from an extra fragment because there's no data associated with them, so there's nothing for you to release. And so it kind of just about hangs together. However, the RX protocol is slightly different. The response structure just has a size field in it. Now, the request, obviously, you push buffers to the back end using requests, and they are full pages. However, obviously, when the response comes back, you need to find out where the back end put the data. Now, there is an offset into the buffer where the back end can tell you where it put the data, but there's no size field. So how do you know how big the data is? Well, that's done magically. The status field can carry a positive or a negative value. If it's negative, that's an error case. If it's positive, it's a size. That's the way that works. The size of the first data frag in this case is actually the size of the fragment. It is not the size of the packet. So to get the size of the packet, you have to add all the frag data together. The extra segments pose a slightly different problem, though, because like with the TX protocol, the ID of the request is echoed in the response. But again, the extra fragments don't have an ID in them. So how do you know which request they correspond to? Now, in this case, the request actually did have a grunt reference in it. It is referencing some resource. The front end has to be able to free that off when the response comes, but it doesn't know where it is. So it actually turns out that in the receive ring, it is required by the protocol that responses must be in the same slot as the corresponding request. So the ID field is actually completely useless in the RX protocol. So the protocol over the years has undergone some changes to improve performance. Originally, it had a single event channel for RX and TX. That's a bit of a problem because if the event channel is pinged by the back end to the front end, how does it know whether it's to do TX completion processing or RX processing? So the only thing it can do is do both. And this is pretty wasteful because generally in protocol stacks, you don't need to eagerly process TX completions, and just polling both rings is relatively slow. So the first sort of extra performance feature that went in was to split the event channels. So there's now a separate event channel, or the option of a separate event channel for RX and TX rings, controlled by that Xen store key there. The next bottleneck is the fact that there was only a single pair of rings. So largely processing ended up being done on a single CPU. Certainly the event channel was interrupted in an individual CPU. And this caused massive load skew in the guest and generally was pretty harmful for throughput. So the next thing that was done was multi-queue. Now that basically gives you the option of having an RX and TX ring pair per guest CPU. And that way you can now load spread your work across all the guest CPUs, which is a massive performance improvement. The next one that's still the product of perennial speculation is whether the single pages for RX and TX rings are actually a bottleneck. Now, I have to say that in the last couple of days, I tried implementing multi-page ring, and it actually made no difference to the performance numbers that I was getting. So I honestly don't think the ring size is a bottleneck for the workloads I was running. However, it might be for some workloads. I do have patches. I will probably clean them up and post them. So on to Windows RSS. Now, about a decade ago or more, Microsoft defined Windows RSS, receive-side scaling. The idea is that the NIC, on receipt of a packet, will calculate a hash over that packet using a key provided by the network stack. It will then use that value to indirect into a table, which is programmed with basically CPU numbers. It will be able to reference a CPU number to a particular MSIX vector that it's been programmed with, and that will allow it to interrupt the correct CPU for the network packet as received. So that way it can spread its interrupt loadout across all the CPUs. Now, this is obviously Microsoft's definition in terms of an ideal piece of hardware. Most NICs implement this because it's so old. So, if you're going to buy a decent NIC, it's going to be able to do this. But how do we do it in PV drivers? Well, in the front end, we already have multi-queue. So we have the ability to have a queue per CPU. We also have a couple of hypercalls there. About a year or so ago, I added the set event upcall vector hypercall that allows you, if you're using FIFO event channels, to steer a particular event channel to a particular CPU, in a particular event channel's particular FIFO's upcall vector to a particular CPU. So now you can create per CPU event channel upcall vectors, and then you can bind event channels to particular CPUs. This allows us to do what we need to do in the front end, but there's a whole, obviously, infrastructure missing from the front end we need to deal with in the back end. So, obviously, we have the packet, the hash, done using the key, and the indirection table. All this needs to be programmed by the Windows network stack, but it's all in the back end. So we obviously have some way, or we need some way of getting the data through. So there's a protocol extension that I implemented. As I said, we need to get the hash algorithm through. It's always toplets as it happens, but Microsoft do reserve the right to specify other ones. They never have, but they could do. A hash key for the flag, for the algorithm, flags to say what types of headers they want you to hash over, and an indirection table, obviously, to steer the particular hash values of the particular packets to particular CPUs. So I introduced the idea of a control ring. So this is in the Netif header file. You can go and look at the documentation I put in for this. We only need one of these between the front end and the back end. It's essentially out-of-band data. It's not performance critical. So we don't need one per queue or anything like that. There is just a single control ring between front end and back end. And those are the defined request and response types that we have at the moment. You can see from the list, basically we have means of querying hash flags, setting algorithms, passing a mapping table through, all the kinds of things we need to do. And then I went ahead, having got agreement from the Xen community on the specification, I went ahead and did an implementation in netback. So in netback we now have an NDO select queue op, which overrides the default op for steering particular packets to particular queues. That entry point essentially just uses the mapping table, calculates a toplets hash and sets it, and then looks up the appropriate queue to steer the packet to from the mapping table. Calculating toplets in software is actually pretty expensive. So one optimization we did was to have a hash cache. So there is a, by default, 64-entry hash cache, where the flow header or the IP TCP header from the packet is just looked up in the cache, and a hash value is pulled out from the cache, because it is actually easier to just match over a potentially up to 36-byte header than it is to actually calculate the hash. So that's an optimization. And typically, if you're running benchmarks, your flows will always fit within that 64-entry table. Over time, it's an LRU table, so over time some will get spilt, new ones will get imported if need be. But it's a reasonable optimization. And there's a module parameter if you want to make the cache bigger. Last week I added a Debug FS node to netback, so now you can see, if you cat that debug node, you can see the algorithm in use, what flags are enabled, and then below that there would be the key value in use and the indirection table as well. But what about the values? So one question is, why did we set the value on the SKB? All we needed to do was look up something from a table. Why did we actually put the value in the SKB itself? Well, the reason for that is that in the actual RX path, I defined a new extra frag type, which contains those fields. So there's the hash type, whether it's TCP or IP, basically, the algorithm used, which is always toplets in practice, and the hash value, which is a 32-bit value. Had to be passed as an array of 4 uint8s because of alignment issues, but it is just the 32-bit hash value. Windows actually requires you to send the hash value up the stack, so this also means we can avoid recalculating the hash in the front end, which is a good thing. And the nice thing is that Windows will then give you that hash value back for the same flow on the TX side, so you can always steer the TX packets for the same flow to the same CPU and keep everything nicely localized, which is good to avoid lock contention. So performance measurements, that's the bit of hardware I ran them on. It's my Gigabyte Bricks box, which is sat on my desk in the office. It's a pretty pokey little thing. It has a tendency to run its fan a lot, which annoys people around me. It could probably levitate itself off the desk when I'm compiling a Linux kernel on it, for instance. But it's a Haswell CPU, 32 gigs of RAM, 200 gig SATA SSD, so it's pretty fast. Choice of software, I use Windows 10 Anniversary Edition, so the latest, greatest. 32 bits, just because I prefer 32-bit. 4 CPUs, 4 gigs of RAM, the latest PV drivers. I was using Xen. I just picked a stable version of Xen, so I just used 470 and the upstream QEMU that came along with that. Linux 470 again, but I added my Debug FS patch, but otherwise it was a straight 470 kernel. And the benchmark I used was Ixia Chariot, because it gives some nice graphs. So first graph there is single flow. So this is just a single pair between two guests running on the bricks. As you can see, we're getting about 8 gigs through on that single flow. So next test was 2 flows. Again, you can see they're reasonably okay. They're not varying too much, and it boosts the performance up to 12 gigs throughput. 4 flows. bit more variance, but you can see they're broadly around the same center line, and we're now running at nearly 17 gigs. So not bad at all, I think. So does RSS make a difference over basic multi-queue? Well, the thing is, you can see those flows are generally balanced around that same center line, so they are reasonably well distributed. And that's the thing that RSS gives you. It allows Windows to redistribute flows if it sees them starting to drift and skew onto particular CPUs. So this was a test I put together where I turned off the RSS and ran tests until I got a badly balanced situation. You can see from the number there that we're already down like 3 gigs on what we were getting with a well-balanced set, and you can see how they're sort of centered around 2 different lines, and the lower set is basically contending on CPU. That's why it's not running so well. So if we synthesize an environment, so I can use RSS to synthesize an environment where all the flows are competing for exactly the same CPU by putting an indirection table in that's full of 1s or full of 0s or whatever. So I did that. So you can see bandwidth all goes down to about 11 gigs. So we're down about 6 gigs on the best case there. So it's a fairly severe performance impact that you get from a badly balanced set of flows. So conclusions from those tests are that that multi-queue does work best if you can make sure that the flows are balanced. Now, standard multi-queue has a static hashing, so you have no way of ensuring that. You just have to be lucky. Whereas RSS allows the guest to control the TCP flow to queue mapping via the indirection table and the hash key. And Windows, if you set the appropriate hash profile, or RSS profile, and Windows will dynamically balance over periods of time. As the traffic changes, it will try to get the best by rebalancing the flows, and you'll get the best out of your multi-queue. So, questions? Like, do you need a mic? Where's the mic? Oh, there it is.
Thanks. So first question is, I have a few questions. I'll split them up if necessary. Why do you need a control ring? The protocol that you define in the control ring seems synchronous, so you could just specify what you want and get a response back synchronously. Is there a need for a ring?
I mean, the original idea was just to do it through XenStore.
Right.
Problem is for certain pieces of data like the mapping table, it's quite large, potentially, and XenStore has fairly severe quota limits. So if you tried to put it through XenStore, you'd still have to pass it a chunk at a time, potentially, and doing that through XenStore gets quite messy. Let me say the original one was just to put it in XenStore straight, but yeah, you can quite easily hit your quota limits if you're not careful.
So in the ring, you're stuffing the actual indirection table in the ring, or
yeah,
you're putting pointers to
the two set hash mapping size, set hash mapping. You can set a size which is like basically arbitrarily big if you want, and you can pass the hash mapping. It's done by passing single page grant references. So you can pass the data page at a time through and reprogram parts of the table. So basically you've got an arbitrarily big mapping table at your disposal if you need it.
The table is passed in the ring?
No, the table itself is not passed in the ring, it's passed by grant reference. So you allocate, you can potentially have a table that's pages and pages and pages long, right, and you can just pass the grant references.
Which you could have done over XenStore as well, right?
You could do that, but yeah, you'd have to basically pass one and then say, okay, sure, I've done that one, pass the next. Sure. It gets a lot more tricky. I mean, essentially, you end up doing a ring-like thing through XenStore anyway.
Okay. Yeah. Are there other questions before I... Okay, next one. Why did you, would you get better performance if you used MSIX like Windows was designed to?
Well, as George alluded to in the talk earlier, if you could use things like APIC-V effectively, then maybe you would get better performance. But I don't know quite how that's going to work with event channels, to be honest. You're still going to have to presumably have the FIFO there. Essentially, it's still a VM to VM interrupt.
Well, so that's the thing is, your performance measurements were VM to VM on the same host. If you actually got traffic coming from the outside over an RSS-capable NIC, you got MSI access coming in.
Well, I mean, obviously, it depends on your situation. I mean, if you've got a one-to-one mapping between your NIC and your VM, then essentially, yeah, you do want the configuration to go all the way out to the NIC.
Right.
You probably won't be using pass-through at that case, in which case you're going to get the best out of APIC-V anyway.
You lose a lot of virtualization benefits.
Yeah, you lose your virtualization. You want to share the NIC, then obviously you can't have one VM in control of the indirection table for the NIC, for instance. What you could potentially do is if they all happen to be using the same hash flags, they all want TCP plus IPv4, then you could try getting the NIC to set that. There's one limitation, though, in Linux is the fact that there's no mechanism by which you can set the hash type on an SKB, so you don't know whether an SKB has been given an appropriate toplets hash or not. All you've got is a bit saying L4 and a bit saying there's a hash there. So that would be extensions to the SKB.
Okay.
Any more? Okay, I think we're probably done then.